Hello, welcome to this new video about electronic simulation of Vishay thermistors and RTDs. My name is LTspice and I'm a product engineer for nonlinear resistors at Vishay. Today we will design a network of PTCEL67, the inrush current limiters high energy, in a battery pre-charge circuit for an automotive application. The PTCEL67 have a higher switch temperature than the PTCEL17. Thus, they can absorb more energy before going to high resistance values. In this simulation, we charge the same capacitor at the same rectified voltage via a 500 ohm PTCEL17 on the right and the same ohmic value of the PTCEL67 on the left. A short charging time of the smooth capacitor is generally better in the pre-charge circuit for an automotive battery. So we will record the time for reaching a voltage level, here 90% of the maximal level, while keeping an eye on the surge current. We performed 30 simulations with a Monte Carlo distribution on ambient resistance tolerance for each PTCEL. Measurement of the charging time shows lower value for PTCEL67, while maximum surge currents are relatively comparable. So in this case, if the charging time is critical, PTCEL67 will be a more efficient solution than PTCEL17. Let us build now the right PTCEL67 network for a similar design. Having to charge now this big capacitor, you have used a value of 500 ohm for the PTCEL in order to limit the current according to your requirements. In the simulation results, you see that the surge currents will always be lower than, let's say, 10 amps, but that the capacitor voltage saturates well under the required charging value because the PTCEL has switched to high temperature. So we need to build a PTC network which will allow this charge while maintaining the same maximal surge current. So we have here 4 possibilities of PTC networks that will be compared with the original single PTCEL circuit, the number 1. Number 2 is 2 PTCEL 1000 ohms placed in parallel. Then 3 PTCEL 1500 ohms placed in parallel as well. And 4 PTCs with a network of 2 parallel branches of 2 components in series. These mountings 2 to 4 will in principle give a 500 ohm at ambient temperature. But PTCL are exotic components. Their values are depending on the applied voltage. So if in mounting 4 the net voltage is divided onto 2 serial PTCs, the decreasing of the resistance of this PTC could be lower. Hence the presence of mounting 4B, identically configured as mounting 4 but with a 250 ohms instead of a 500 ohms. We will record now the voltage variations around the capacitors, cap 1, 2, 3, 4 as well as 4B. And we visualize also the reach temperature for the PTCs. The race is begun. The winner will be the one that will reach the threshold voltage the first. As usual, it's a Monte Carlo distribution overall, also for the capacitor value. So 10 simulations are being made. We see that in the first second, the solution 4B has already an advance on the other mountings. And indeed, after 3 seconds, the threshold voltage is reached. Solution 2, 3 and 4 are following next, while the one-element PTCEL is last. The winning ticket is confirmed by the 9 other simulations. The network of 2 branches of 2 serial PTCEL67 250 ohm is thus the fastest solution. We see also that the final PTC temperature decreased significantly with an increasing number of pieces in the network. We perform the measurement of the surge current and the charging time, and after plotting this measurement, we see that all the values of the surge current are under 10 amps and that the surge currents are especially low for the solution 4 PTC 500 ohm. In this case, the voltage-dependent effect on the resistance was lower and thus the surge were lower as well. For the charging time, it is clear that the shortest time is really reached with a network of 4 times 250 ohms. So, this is a winner. Now we have the possibility to test extensively with 100 runs this time and confirm that the surge will always be lower than 10 amps and that the charging time at 90% will swing from 2.6 to 5.2 seconds. As a last step, do not forget afterwards to verify in the real world the conclusions of the simulations. Well, that's it for the moment. I hope that you enjoyed the video. Thanks for watching.